Non-homogeneous linear equations. If in a linear equation f of d d dash of z f of xy, the polynomial expression is not homogeneous, then the differential equation is called a non-homogeneous linear partial differential equation. That is, the order of the derivatives vary in a non-homogeneous linear partial differential equation. Its solution can be found by using complete solution equal to complementary function plus particular integral. Now the methods of particular integral are the same as that of homogeneous equations, which we have learnt in our homogeneous equations video. But to find CF, we factorize f of d d dash into factors of the form bd minus ad dash minus c. Then CF can be found corresponding to a non-repeated factor bd minus ad dash minus c. If it is non-repeated, then the part of CF is e power cx by b f of by plus ax. Corresponding to the repeated factor twice, if this factor is repeated twice, then CF is e power cx by b f1 of by plus ax plus x f2 of by plus ax. Okay. Next, corresponding to a factor ad dash plus c, CF is e power minus cy by a phi of ax. If this factor ad dash plus c is repeated twice, then CF is e power minus cy by a phi 1 of ax plus x phi 2 of ax. Now corresponding to a factor bd minus ad dash, CF is f of by plus ax. But if this factor bd minus ad dash is repeated twice, then CF is f1 of by plus ax plus x f2 of by plus ax. Now corresponding to a factor d dash, the part of CF is f of x. But if it is repeated twice, if d dash is repeated twice like d dash square, then CF is f1 of x plus y f2 of x. Corresponding to a factor d, CF is f of y, and corresponding to d square, it is f1 of y plus x f2 of y. Okay. Now problems. Solve 2 dou square z by dou x dou y plus dou square z by dou y square minus 3 dou z by dou y equal to 5 cos 3x minus 2y. So here we can observe that the equation has second order derivatives as well as first order derivative, hence it is non-homogeneous. Therefore, we should use the rules of non-homogeneous linear partial differential equation. Solution. Given this equation, so first we should write the equation in the operator notation. So after writing in the operator notation, we should bring it to the form of bd minus ad dash minus c. Okay, so therefore we see that d dash is common. Okay, so we take d dash common and remaining terms are 2d plus d dash minus 3. So it is in the form of bd minus ad dash minus c, where b is equal to 2, a is equal to minus 1 and c is equal to 3. Okay, and corresponding to d dash, CF is f1 of x. Alright, so corresponding to 2d plus d dash minus 3, CF is e power cx by b f of by plus ax. So here it is e power 3x by 2 f2 of 2y minus x. Alright, so that is the CF. So together CF is, for d dash it is f1 of x, and for this function we have written a different CF. Hence together CF is f1 of x plus e power 3x by 2 f2 of 2y minus x. And then we will proceed to find the particular integral. Particular integral is found in the same way as that of homogeneous function. So here we have cos of 3x minus 2y. So we should put d square equal to minus a square. So there is no d square here. And then d dash equal to minus ab, d dash square equal to minus b square. So d dash is minus of 3 into minus 2, that is 6. D dash square is minus of minus 2 whole square. Okay, so particular integral is 5 into 1 by 2 into 6 minus 4 minus 3 d dash cos 3x minus 2y. 5, that is equal to 5 into 1 by 8 minus 3 d dash into cos function. But now whenever it is cos function, and we have d dash term or d term, we have to rationalize to get d square or d dash square. But here we have d dash, so to get d dash square, we will rationalize. So we'll get 5 into 1 by 8 minus 3d dash into 8 plus 3d dash by 8 plus 3d dash cos of 3x minus 2y. Thus, solution is 5 into 8 plus 3d dash by 64 minus 9d dash square cos of 3x minus 2y. Hence, substituting for d dash square as minus b square, it gives minus 4, and simplifying, that gives us 5 by 100 into 8 plus 3d dash cos of 3x minus 2y. Now removing the brackets, 8 into cos is 8 cos 3x minus 2y plus 3 into d dash of this function. D dash is dou by dou y. So differential of cos function partially with respect to y. That gives us minus plus 3 into differential of cos is minus sine 3x minus 2y into differential of 3x minus 2y partially with respect to y is minus 2. Simplifying, we get the particular integral. So that is the particular integral. Final solution is complementary function plus particular integral. Now next problem, solve dou square z by dou x square minus dou square z by dou x dou y minus 2 dou square z by dou y square plus 2 dou z by dou y plus 2 dou z by dou x equal to e power 2x plus 3y plus sine 2x plus y plus xy. Okay, now let us solve this equation. That is, here we have to solve first to find the complementary function. So let us group the terms. Minus d dash can be written as minus 2d dash plus d dash. Okay, so here we'll take d common for the first 3 terms. For the next 3 terms we'll take d dash common. Thereby we get d into d minus 2d dash plus 2 plus d dash into d minus 2d dash plus 2. So writing the factors, it gives us d plus d dash into d minus 2d dash plus 2 into z equal to the right hand side. So remember, here we are not going to write any auxiliary equation, but rather corresponding to the factors we are going to write the complementary function. So corresponding to d plus d dash, it's in the form of bd minus ad dash. Okay, so therefore complementary function is f of by plus ax. So a here is minus 1. Therefore CF is f1 of y minus x. Corresponding to bd minus ad dash minus c, complementary function is e power cx by b into f of y by plus ax. So writing the values, here b is 1, a is 2, c is minus 2. Okay, substituting, we'll get e power minus 2x f2 of y plus 2x, and the other complementary function added together gives us the complete complementary function. Now further, to get the general solution or the complete solution, we should find the particular integral corresponding to the right hand side functions. The right hand side has e power 2x plus 3y, okay, and sine of 2x plus y and xy. So first let us find it for e power 2x plus 3y. So whenever we find for exponential function, we should write the denominator in terms of factors to check if we are getting any zero terms. So here we are writing it in terms of factors and we do not get any zero terms. So that itself is the particular integral. That is, we substitute d equal to a and d dash equal to b. Okay, a is the coefficient of x, b is the coefficient of y. Next we proceed to find the particular integral of sine of 2x plus y. So for sine of 2x plus y, for d square we will substitute minus a square, d dash square equal to minus b square. Okay, so therefore it gives us, by substituting for d square and d dash square and d dash, we'll get the remaining terms, that is 1 by 2 into d plus d dash sine of 2x plus y. But here we have to rationalize the function. So we are rationalizing by multiplying and dividing by its conjugate, that is d minus d dash. That gives us 1 by 2 into d minus d dash by d square minus d dash square sine of 2x plus y. That is 1 by 2 into d minus d dash by minus 4 minus of minus 1 sine of 2x plus y. Okay, so substituting the terms in the denominator, we are now left with the numerator term where we have to apply the constants, where we have to apply the derivatives. So d of sine of 2x plus y minus d dash of sine of 2x plus y is what is left. So d of sine of 2x plus y is 2 cos 2x plus y minus cos 2x plus y is what we will get as the particular integral into minus 1 by 6. Now corresponding to the third term, that is xy, particular integral is 1 by d plus d dash into d minus 2d dash plus 2xy. So whenever we have xy is a polynomial, we write f of d dash as 1 by f of d dash as f of d dash inverse. Okay, so that is what we are doing here. So first we'll apply it for the first factor. Thereby we'll get 1 minus d dash minus d by 2, okay, inverse into xy. So what happens here, we have to expand it. So when we expand, we have to expand using 1 minus d inverse. So both the signs are minus, we get a positive series. Alright, and we should apply these terms. When we apply it, we'll get 1 into xy is xy, d dash into xy is d dash is, yes, d dash minus d by 2 into xy will give us the remaining terms, that is xy plus x minus y by 2 minus 1. Okay, so remove the brackets 1 by 1 and apply it to xy. Further, 1 by 2d, here we are taking d common, so 1 by 2d into 1 by 1 plus d dash by t into the function that is obtained in the previous step. Take the inverse, expand it, so signs are alternating, we'll get an alternating series, and once that is done, apply it to the function. Alright, when the remaining terms become 0, you can ignore those terms. Apply to the function. Finally, we get a function, and for that we should apply 1 by d. 1 by d means integration with respect to x. So having done that, we will get z function, that is the particular integral. Add all the particular integrals and write the solution. So that gives us z equal to complementary function plus particular integral.